Up until now, we've only compared mu or p to a value. Maybe that other value is another mu or another p, but everything has been constant. But what if the mu's are not constant? What if mu can vary, in this case from 75 to 95, being the total height of part of the arm, versus another variable which can also change, for instance, the total length of a head. In that case, we have to do regression. Now, regression is a graduate school concept, and we're just going to introduce it. Initially, you need to understand what a two-dimensional chart looks like. Now, you guys have all had algebra, at least at some point in your life, so you probably are aware that this is a graph that relates an x variable to a y variable, where x is considered the input. It also can be considered an independent variable, and we say it's independent because we can allow x to be whatever it wants within this range. But once we've defined what that x should be, there should only be one corresponding y variable, or an output. I like to think of it as like you put money in a Coke machine and you press the Coke button, you expect to get a Coke that comes out. You press the cherry Coke button, you expect to get a cherry Coke out. So you choose the input and you're guaranteed the output. In the vending machine example, the button you press is the input, and the can of soda you get out is the output. So the output absolutely depends on the input, and therefore is the dependent variable. Taking a look at this graph, we don't really see a line though, right? We just see a collection of dots. But we can still draw a line through these dots that summarizes what these dots are doing, right? These dots are clearly going up, and they kind of go up with this slope. Now, you might draw it that way, you might draw it this way, you might draw it that way. How do you know which of these is correct? Well, that has to do with what type of regression tool we use. Since we have a calculator, it does it for us. So let's just go with this one. So if we had an input variable of, say, this is around an 89, then we could draw this up to our regression line, and where it intersects the regression line is where we draw to the left until we find our corresponding output variable. So in this case, an x of, say, 89 might represent a y of 94. That's as far as we're going to go with the discussion on scatter plots. As you can imagine, these dots don't always have to go up. They can sometimes go down, and sometimes they just kind of don't do anything. So this downward graph we call a negative correlation. This also has a negative correlation, but can you see that the points are closer together? So this is a tighter negative correlation. And if there really is no correlation, the points just look like a big blob, then we say that there is no correlation. So if we have a correlation, whether it's positive or negative, we can find an equation of that line, and that takes the form y equals mx plus b. B is the initial amount, or the y-intercept, and m is the slope, or the rate. X we've already defined as the dependent variable, y is the independent variable. So we might have an equation y equals 20x plus 5, and so therefore if x equals 10, y would be 20 times 10 plus 5, or 205. The independent variable, x equals 10, produces a dependent variable, y, of 205. On some introductory statistics math tests, you may be given an equation, given an independent variable, and asked to predict the dependent variable. That's how statisticians call it. You might also be given a graph with a regression line drawn through it and asked, hey, if X is 95, what do you predict Y should be? Or they want to be even more tricky. They may say if the total length is 95 for a bushtail possum, then predict what the head length would be. And you'd go, okay, well, if it's a total length of 95, I draw a line up until it intersects the regression line, then I draw a line over until it intersects the y-axis, and I would say, oh, if I'm given a possum length of 95 centimeters, I can use the regression line to predict a head length of perhaps 97 millimeters. Now let's do some different types of correlations. Here we see a correlation that goes up, and all of these actually go up. But you can note that there is a change in the strength of the correlation. This is an obviously perfect correlation. This might be what you see if you're trying to do physics problems, because physics always follow a perfect mathematical formula. This might be if you're trying to, maybe do a physics problem, but there's some slight variation. Sometimes it's a little bit too much friction, or sometimes a little air resistance. Very, very strong correlation. This is what you normally see in a strong statistical result, like household income and value of the home. Right? A family who has a lower income is going to probably have a lower value home, and a family who has a very high income is probably going to have a higher value home. But there's some discrepancies. You can maybe inherit a home, or maybe you have some hard time with credit, and so you can't get the home that you actually can afford. And then you'll see ones like this, which I drew it pointing up, but really you don't have any idea where this is going because it really kind of just looks like a blob. And so in general, if R is low, like around 0.3 or lower, I like to say less than around 0.4, then there is no correlation. If R is above 0.4, but not much higher, if R is above 0.4, but not much higher, perhaps below around 0.7, then we say that's a good correlation, right? It's moderate, it's good. But if it's above 0.7, like in this case, 0.98, then we say it is a strong correlation. So this is a weak correlation, this is a good correlation, and this is a strong correlation. So when you're talking about data on a scatter plot, you have to talk about two things. One is it positive or negative? These are all positive. And the next is how strong or weak is the correlation. So you can see here, this looks like a blob, so it is a weak correlation. This is a little stronger, right? Actually much stronger, negative 0.64. Now, what does the negative mean? It just means it's a negative correlation. As you increase the x, the y goes down. So this might have to do with, let's say you have people running, and this is how much muscle mass you have or how in shape you are. So if you're not in shape and you run, you're going to have a very high heartbeat, right? But if you are more and more in shape, have more and more, lean to body fat or whatever it is, you might have a lower heartbeat after running. This is an even stronger negative correlation. Think of playing golf. The better you are at playing golf, the lower your score gets. And this is a perfect correlation, but it is negative. Negative doesn't mean bad. Negative just means that it's going down. As you increase the independent or the x variable, the y variable, the dependent variable goes down. So on a test, you would be given these different graphs, and you'd be given different r's, and you would have to match the r with the graph. I won't ever ask you to predict exactly what the R is, but if I gave you these 4 different R measurements, you should be able to line them up with the corresponding graph. Now let's do an example. This is about gift aid and family income. So gift aid from a university. So a family that has very little income is going to receive a lot of gift aid from the university. But a family who has a very high income, $250,000 a year, is going to receive less gift aid from the university. It's asking us to use this model to predict a family's aid if they have an income of $1 million. Now, this is kind of a tricky question because you don't see 1 million here, but notice that we are dealing in thousands. 1 million is equal to 1,000 thousands. Now you might look and go, well, wait a minute, Tua, I don't even see 1,000 here, and you would be right. We would have to extend this graph all the way out, right? And if you do that, you would see that 1 million is way off the chart. So we would predict 0 gift aid off the chart. But we can also use this equation. So the equation says the aid is equal to 24.3 minus 0.0431 times the family income. In this case, we have to say it's 1,000 because 1,000 is 1 million. So let's use our calculator to determine the actual aid, gift aid received according to the equation. Well, we can maybe do this in a row. 2.43 minus 0.0431 times 1,000. When we hit enter, we say, look, they actually get negative aid. That means if you make $1 million or more, you have to actually pay the university even more money on top of the tuition. Of course, that's not right. And that just shows that regression only works for local variables. Right? This only works for family incomes between 0 and maybe 300,000. If your family makes more than that, we can't use this regression. That doesn't mean that regression is a lie and can't ever be used, but like with everything, just because you have a hammer doesn't mean everything around you becomes a nail, right? A hammer can only be used on nails. Regression can only be used within the domain or the possible independent variables. All right, so this will be your homework. First thing you're going to do is determine whether it's a positive or negative correlation. So I'll give you a hint. B is positive correlation, but you've got to figure out for all of these. Now, if you're unsure or it doesn't make sense, then you would say no correlation. So I'll give you another hint here. This is no correlation because it goes negative and then it comes positive. That means no correlation. The other hint is a lot of these are no correlation. So if there's no correlation, you don't even have to say what the strength is because there isn't even a correlation. So if there is a correlation, you have to identify it as weak, good, or what we call here is moderate or strong. All right. So this one would have no correlation. You don't have to say that it's weak, moderate, or strong. This one, since it's positive, you have to determine if it is weak, moderate, or strong as a positive correlation. This is what I was talking about, matching R value to a graph. And I'll give you another hint. When you see something like this, where there's no correlation means close to 0. A good correlation, a strong correlation, is close to 1. So this would represent a strong correlation. And this here, because it's close to 1 on the opposite end, or negative 1, this also represents a strong negative correlation. And last one is an actual word problem. This is a relationship of height versus weight. And here you need to understand the variables here. This is your y-intercept. So remember, you have y equals mx plus b. So the intercept here is your b, your B. And this here that just says height with nothing next to it, this represents your M. So when you make your equation, you'll use these two numbers for M and B. And then you'll just leave y and x as y and x. So you'll have to describe the relationship, meaning is it positive or is it negative, and the strength. You'll have to write the equation, which is this, with the numbers substituted. And then we'd like you to actually do a regression. Now, before we did regression, what did we look at? P-values. Well, this is the p-value. So we always focus the p-value on the slope, because if the slope exists, then it should have a strong p-value. And so I'll let you figure this out. I mean, you need to come into discussion, but the hint is the way we use p-values in regression is the same we've always used p-values. So you got to know, hey, is the p-value of 0 really good or not really good? Now, the null and alternative hypotheses for all regressions are usually the same. The slope, or M, for the null hypothesis is always equal to 0, meaning there's no correlation. And the alternative is the slope should either be greater than or less than 0. We don't have a not equals to in this case. The slope is either going up or it's going down. And so this would be that there is a positive or negative correlation. So the interpretation, if you had a high or low p-value, would be to write the null hypothesis or the alternative in words. So when I say state your conclusion, we don't just say, oh, retain the null hypothesis or reject it. No, what does it mean in this example? If we retain the null hypothesis and the slope is 0, what does that mean in terms of body measurements? If instead we reject the null hypothesis and we go with the alternative, what does a slope of greater than 0 or less than 0 mean in this example? And that's it, my friends.